Welcome to EPG Pathshala. In our last module, we have seen delta theorems of higher orders depending on the existence of non-zero derivative of some g function, but in practice we can have random vectors and we may require to find the large sample distribution of some g function of a random vector, and in this module we shall discuss such delta theorems considering random vectors. Actually, we start with some interesting facts about the delta theorems what we have discussed in our last module. We shall assumed the scaling factor as square root of n in throughout our last module, and in this module we shall show the different choices of scaling factors for delta theorems, and finally we shall give some examples on the choice of scaling factors and delta theorems concerning multivariate random variables, and of course give some discuss some possible issues with this type of delta theorems. So in this module we shall discuss some possible issues with univariate delta theorem, and then pass on to multivariate delta theorems and provide some examples of these theorems. So first of all, let us start with some interesting issues with delta theorem. For delta theorem, we find that if square root of n multiplied by Tn minus theta converges in distribution to a normal distribution, then under certain conditions the large sample distribution of Gtn is asymptotically normal. So in this case, the first derivative, the square of the first derivative of g dash theta multiplied by sigma square is called the asymptotic variance of Gtn. However, the relation that average variance of Gtn equal to limit n tends to infinity n times variance of Gtn may not always hold. So for example, consider IID sequence of normal variables with mean and variance both unity, and consider Tn as x bar. Then it is an easy consequence of CLT to find that the distribution of square root of n multiplied by Tn minus 1 is converges to a standard normal variable, and as a consequence, if we define Gtn equal to 1 by Tn, then from the delta theorem we find that the average variance of 1 by Tn is nothing but 1. However, exact calculation shows that variance of 1 by Tn, that is the variance of an inverse Gaussian distribution, does not exist, and hence we get what we have discussed earlier. So finally, the relation that average variance of Gtn equal to limit n tends to infinity n times variance of Gtn may not always hold. Actually, there are examples, so many examples. We have given some single example. Actually, there are so many examples where this relation does not hold. Next, we pass on to an interesting aspect of delta theorem. For univariate delta theorems, what we have discussed so far, we have assumed the scaling factor square root of n. That is, we have used square root of n Tn minus theta converging in distribution to some having some distribution x, large sample distribution x, and then obtain the large sample distribution of square root of n Gtn minus g theta. So throughout our previous discussion, square root of n is used as a scaling factor, but in practice scaling factor may be other than square root of n. So the best way is to give some examples. Suppose xn are IID rectangular 0 theta variables, and let x ordered n denote the largest order statistic. So define yn as n times theta minus x ordered n. Then the distribution function of yn is nothing but 1 minus x divided by n theta whole to the power n, which is an ordinary sequence, and it converges to 1 minus e to the power minus x by theta for all x as n tends to infinity. Therefore, since 1 minus e to the power minus x by theta is the distribution function of an exponential random variable with mean theta, we find that the large sample distribution of n times theta minus x ordered n is exponential with mean theta. Thus, in this case, we get a scaling factor n instead of the usual square root of n. It can be shown that if we use the scaling factor square root of n in this case, the asymptotic distribution may not be exponential, it might be some degenerate distribution. So naturally, the already discussed univariate delta theorems are of no use in finding the asymptotic distribution of some function g x ordered n if the scaling factor deviates from square root of n. So we need some generalized delta theorems to tackle this problem. So let us introduce the univariate delta theorem of first order using general scaling factor. Consider a sequence of random variables xn such that an multiplied by xn minus theta converges in distribution to x for some positive sequence an, and it is also assumed that an diverges to plus infinity. Let g theta be a real valued function such that the first derivative of g theta is continuous and non-zero in a neighborhood of theta. Then an multiplied by gxn minus g theta converges in distribution to a random variable which is the first derivative of g multiplied by x. So as a proof, first of all we note that since an multiplied by xn minus theta converges in distribution to x, then we at once have xn minus theta converges in distribution to 0, converges in probability to 0, and using Taylor expansion we have the representation that an multiplied by gxn minus g theta equal to an multiplied by xn minus theta into g dash theta plus small op1. Since an xn minus theta converges in distribution to x, we have an gxn minus g theta equal to an xn multiplied by xn minus theta multiplied by g dash theta plus big op1 multiplied by small op1. Since the product big op of 1 and small op of 1 is nothing but small op of 1, we find that an multiplied by gxn minus g theta is equal to an multiplied by xn minus theta multiplied by g dash theta plus small op1. Now small op1 converges to 0 in probability, and hence applying Slutsky theorem as earlier, the result follows. So we have proved univariate delta theorem using some general scaling factor an. Next we shall extend our delta theorem for higher order in case of general scaling factors. Consider a sequence of random variables xn such that an multiplied by xn minus theta converges in distribution to x as n tends to infinity, and let g theta be a real valued function such that the derivatives of g theta up to order m minus 1 are all 0, but the mth order derivative of g theta is not equal to 0. Then as earlier, m factorial multiplied by an to the power m multiplied by gxn minus g theta converges in distribution to a random variable which is x to the power m multiplied by mth order derivative of g theta. The proof of the above is an easy consequence of Taylor's theorem of higher orders with random variables, and can be proceeded as earlier, and hence we are not giving to details. So let us consider some examples. Suppose xn are IID as rectangular 0 theta where theta is positive, and we are interested in some function g which is defined as log of x ordered n. So it is already known that n times theta minus x ordered n converges in distribution to some exponential random variable with mean theta. So we define gx as log x, and since g dash x equal to 1 by x which is not equal to 0 at theta because theta is assumed to be positive, then we can apply delta theorem of the first order, and we get that n times log theta minus log x ordered n converges in distribution to x divided by theta, where x has an exponential distribution with mean theta. Since for an exponential random variable x by theta has a standard exponential distribution, we have that the asymptotic distribution of n times log theta minus log x ordered n is standard exponential. So now we pass on to our next topic, which is on delta theorem for multivariate case. So consider a sequence of p component random vectors xn and a fixed p component vector theta such that an multiplied by xn minus theta converges in distribution to some p component random vector x as n tends to infinity. Let g theta be a real valued function such that the gradient vector is continuous and is non-zero in some neighborhood of theta. Then an multiplied by gxn minus g theta converges in distribution to some random variable which is defined as the transpose of the gradient vector multiplied by x, that is the limit random variable is the scalar product of the gradient vector of g at theta multiplied and x. So, for a proof, first of all assume that absolute value of xn minus theta in this case denotes the Euclidean distance, that is xn minus theta, absolute value of xn minus theta is nothing but square root of summation I from 1 to n xin minus theta I whole square. Now assume that the gradient vector is continuous in the neighborhood some epsilon in the neighborhood absolute value of x minus theta less than epsilon. Then for absolute value for x minus theta, absolute x minus theta less than epsilon, using mean value theorem, we have gx minus g theta equal to x minus theta multiplied by integral 0 to 1 g dash theta plus t multiplied by x minus theta dt. Actually this is the multivariate extension of Taylor's theorem, some multivariate extension, and this theta plus t into x minus theta is some quantity lying between theta and x. So from this analogy one can find the usual forms of Taylor theorem. So as a consequence of the fact that an multiplied by xn minus theta converges in distribution to x, we have that for every delta greater than 0 probability that absolute value of xn minus theta less than delta is nothing but probability an multiplied by absolute value of xn minus theta less than delta multiplied by an, and due to convergence in distribution of xn we get this probability tends to 1, and hence xn tends to theta in probability. Now for absolute value of x minus theta less than epsilon, we have the representation that an multiplied by gxn minus g theta equal to an multiplied by xn minus theta multiplied by integral 0 to 1 g dash with argument theta plus t into x n minus theta dt, where due to continuity and the fact that xn converges in distribution to xn converges in probability to theta, we have integral 0 to 1 g dash theta plus t multiplied by xn minus theta dt converges in probability to g dash theta. Actually for fixed t and for fixed theta, theta plus t times xn minus theta converges in probability to theta, and then applying continuous mapping and some other necessary results, we find that this integral ultimately converges to the first derivative of g. Thus we have for vector valued random variable an multiplied by gxn minus g theta converges in distribution to transpose of the gradient vector of g multiplied evaluated at theta multiplied by x. In this case one should note that we have used the notation g dash. Actually g dash in this case indicates the gradient vector of g evaluated at what is given in the text. So we need not to confuse about using the g dash theta and delta g. So often we have the limiting random variable of the original random variable or original sequence of random variable as normal p-variate normal with mean 0 and dispersion matrix sigma. Then from the properties of linear functions of multivariate normal variables, we have the large sample distribution of an multiplied by gxn minus g theta as normal with mean 0, variance, transpose of gradient vector evaluated at theta multiplied by sigma, whole thing multiplied by the gradient vector of g evaluated at theta. So this follows from the fact that every linear function of a multivariate normal random variable is univariate normal. So using this result we at once get the mean vector and a variance for the limiting distribution. So now we are in a position to discuss some examples regarding this multivariate CLT and delta theorem using for random vectors. So first of all, suppose we have T1n and T2n such that square root of n, T1n minus theta 1, T2n minus theta 2, that is we are considering the random vector with two components T1n minus theta 1 and T2n minus theta 2, and the vector multiplied by square root of n converges in distribution to a bivariate normal distribution with mean 0 and dispersion matrix sigma. And we are interested in the asymptotic distribution of G, which is defined as T1 multiplied by T2. So assume that Gxy is a function of the real variables x and y, is continuous and has continuous partial derivatives in the neighborhood of theta 1, theta 2. Then by the delta theorem for multiple random variables, the asymptotic distribution of the product T1n, T2n is normal with mean theta 1, theta 2. Now the gradient vector of G evaluated at theta 1, theta 2 is nothing but a two component vector with first component as theta 2 and second component as theta 1, and hence after a little bit calculation, little bit algebra, the asymptotic variance comes out as theta 2 square multiplied by sigma 1 1 plus 2 theta 1 theta 2 multiplied by sigma 1 2 plus theta 1 square multiplied by sigma 2 2 whole thing divided by n, where sigma ij are the elements of the original dispersion matrix sigma. Next, consider our next example. As earlier, we have two random variables T1n and T2n such that the vector with the components T1n minus theta 1 and T2n minus theta 2 multiplied by square root of n has a stable bivariate normal distribution with dispersion matrix sigma. And in this case, suppose we are interested in the asymptotic distribution of the ratio, that is T1 divided by T2. So assume that Gxy is a function of the real variables x and y, is continuous and has continuous partial derivatives in the neighborhood of theta 1, theta 2, except for y equal to 0, because for y equal to 0 this Gxy, that is x by y, is not defined. Thus if theta 1, theta 2 are such that theta 2 not equal to 0, then the asymptotic distribution of T1n divided by T2n is normal with mean theta 1 by theta 2. However, the gradient vector of G at theta 1, theta 2 is nothing but a vector with first component as 1 by theta 2 and second component as minus theta 1 divided by theta 2 square. Consequently, the asymptotic variance comes out as theta 1 by theta 2 whole square multiplied by sigma 1 1 by theta 1 square minus 2 sigma 1 2 divided by theta 1 theta 2 plus sigma 2 2 divided by theta 2 square whole thing divided by n. Of course, this relation is defined only when theta 2 is not equal to 0 and sigma ij are the elements of sigma. So consider our next example. Suppose we need to find the large sample distribution of sample variance. Suppose xi are IID random variables with mean mu and variance sigma square, and we assume that the fourth order moments of xi are finite. So without any loss of generality, assume that mu equal to 0 and sigma equal to 1. Note that the sample variance S square is defined as 1 by n summation xi minus x bar square, can be expressed as 1 by n summation xi minus mu whole square minus x bar minus mu whole square. Thus, we have two distinct random variables. One is 1 by n summation xi minus mu square and the another is x bar minus mu square. So we start from the joint distribution of T1n, which is defined as 1 by n summation xi minus mu, that is x bar minus mu, and T2n as 1 by n summation I from 1 to n xi minus mu whole square. Then it follows from a multivariate CLT that square root of n multiplied by the vector with components T1n minus theta 1 and T2n minus theta 2 is bivariate normal with mean 0 and dispersion matrix sigma, where sigma is given as is a symmetric matrix with first row as mu2 and mu3 and the second row has the elements mu3 and mu4 minus mu2 square. It should be noted that in this case although we have used theta 1 and theta 2 for general definition, but in this case theta 1 is 0 and theta 2 is sigma square. Now at this point it is very interesting to note that the off diagonal element for sigma is mu3. So how does this come? Actually xi minus mu whole square and xi minus mu, these variables are correlated. So the covariance between these two, that is xi minus mu and xi minus mu square, is nothing but mu3, and we get this quantity as the off diagonal element of sigma. Similarly, when we find the variance of T2n, we find that variance of T2n is nothing but variance of x1 minus mu whole to the power 4 divided by n, and variance of x1 minus mu whole to the power 4 is nothing but mu4 minus mu2 square, and therefore we get the lower diagonal element of sigma in this way. Now let us get back to our original problem, that is finding the large sample distribution of s square. So we define gxy equal to y minus x square, then gxy is continuous and has continuous partial derivatives in the neighborhood of theta 1 theta 2. Since the gradient of g at theta 1 theta 2 is a vector with elements 0 and 1, we find that this gradient vector is non-zero, and we find from the delta theorem with multiple variables that square root of n s square minus mu2 converges in distribution to a normal variable with mean 0 and variance as given in the text. Now after a little manipulation, we find that the asymptotic variance, which is expressed as a quadratic form, is expressible as mu4 minus mu2 square. So if the underlying distribution is normal, then mu4 equal to 3 times sigma to the power 4, and hence in such a case the asymptotic variance reduces to 2 times sigma to the power 4. As an easy consequence of the delta theorem, we find that square root of n s minus sigma converges in distribution to normal distribution with mean 0 and variance mu4 minus mu2 square whole thing divided by 4 times mu2. Actually we have discussed large sample distribution of s square, and then s is a function of s square, and using our original delta theorem for univariate setup we get this distribution, and under normality we find that square root of n s minus sigma converges in distribution to a normal variable with mean 0 and variance sigma square by 2. So we have just seen how delta theorems are important in statistical literature, and we have just seen how delta theorems for vector valued random variables can be used to find some sample summary measures. We have obtained the large sample distribution of sample standard deviation and sample variance using this method. In our next module, we shall discuss delta theorem for vector valued functions g, and this result we shall see will enable us to find the large sample distribution of sample moments and some functions of it. And as for example, we have functions like sample coefficient of skewness and sample coefficient of kurtosis. However, we start the module with large sample distribution of coefficient of variation.